So that session is going to be about building a serverless data lake on AWS. And serverless is exactly what we need to discuss right now, because most of you are probably aware that we actually released the AWS Lambda, our serverless compute service, last Friday. It's available in the Sydney region now. Just a reminder, this is a 301 session, but I would expect that by this time of the day, everybody is at the 300-400 level. I can see on the faces you all are at 400 level. So my name is Sebastian Menent. I'm an enterprise solutions architect based in Sydney. I will be joined later on stage by my colleague Namjit Cho. We'll actually provide a demo of what we're about to discuss, and Chris will rock up and share some amazing stories with you. You know it's a 300. It's not too late to leave if you want, but if you leave, I will actually put your name down. The agenda for today. We are going to actually ask ourselves, what is a data lake? Then we will try to understand why you need a data lake. I will share with you some best practices of how building your data lake on AWS. We will have the demo and our customer story, and then we will discuss about the next steps. So first of all, the real question here is, what is a data lake? So like all very important questions in this world, Wikipedia to the rescue. We get a definition that we will read together. A data lake provides massive storage for any kind of data, enormous processing power, and the ability to handle virtually limitless concurrent tasks or jobs. So I don't know if actually the accent is making it more confusing, but it doesn't really mean anything. Would you agree? It's a bit fluffy. So let's try to actually put some characteristics around what a data lake is. So first of all, a data lake should have one key attribute, the ability to collect everything. And by this, we actually want to be able to land into our data lake any type of data, any format of data, in their raw source or in their processed form. As well, we want to be able to dive in anywhere. We want to actually enable any teams across the organization to get access to that data, be able to analyze that data, to actually enrich that data on their terms. And most importantly, we want to have a flexible access to that data. We want to be able to actually come and analyze that with in-memory processing, with Spark streaming, and we want to maybe use Hadoop, Pig, Hive, all these great things for big data, but at the same time, you may want to use your traditional business intelligence tools, like Tableau or Business Objects, so we will actually discuss how you would do this. So, first and foremost, why do you need a data lake? I'd like to discuss a very important concept when we're talking about water, the Olympic swimming pool. And you're there thinking, what has it got to do with a data lake? Well, when you see an Olympic swimming pool like that, it's actually very shiny when it's newly built, and it's very well designed for a very specific purpose, which is going to actually go back and forth at the speed of your liking. But there are very clearly defined rules to use it. You actually need to stick to your lane. You need to use compliant swimwear. And if you actually were to renovate it or actually extend the size of that Olympic swimming pool, you probably will have to engage the original builders, and it's going to be like a multi-million-dollar project. And I don't know for you, but it kind of reminds me a bit of the traditional enterprise data warehouse, especially if you're talking about hardware appliances. They're actually very good for what they do. They've been designed for high-speed analytics. And you'll be able to do all sorts of business intelligence with them. But if you actually want to grow their size, first of all, you actually will reach a limit, and there's only so much you can do with it. And it doesn't really enable you for modern business needs that have actually been coming out in the last 10, 15 years. So I'm thinking things like machine learning, in-memory processing, predictive analytics. And these things that are actually really much data sciences coming with the cloud, they've actually been enabled for over a decade by big data tool sets coming out of the Hadoop ecosystem. So our friendly elephant has actually been providing things like MapReduce and Hive and Pig and Presto and all these tool sets that actually allow us to analyze unstructured data. But then we are in a situation where on one end, we actually have the Hadoop ecosystem, that is available on AWS with Elastic MapReduce. That's great for unstructured data. Think about maybe server logs or IoT devices outputs and things like that. And then on the other hand, we've got our enterprise type data warehouse that you can actually access on AWS using a technology like Redshift. But neither of them is actually going to be our data lake, because one technology is actually very well designed for structured data, while the other one is very well designed for unstructured data. And you don't want to keep your unstructured data into your data warehouse, even if actually Redshift is a petabyte scale data warehouse. There's only so many meaningful things you can store in there. And at the same time, you don't want to keep all your data into your Hadoop cluster nodes, because in terms of cost, it's not going to be fantastic. So the solution to this is actually to augment this by the addition of a great data lake. I wish actually technology was always so peaceful. The great thing about having a data lake in there as well is the ability to decouple compute and storage. So on one hand, you will be able to actually grow your storage almost infinitely, and you will be able to actually run your compute task on top of the data lake. You can actually run lots of nodes for compute, so lots of technologies on top. And then you can actually shut it down when you're done using the compute, so you only pay for storage. One analogy for this would be the combination of Elastic MapReduce sitting on top of Amazon S3, and it actually connects with a technology we have called EMRFS. So the new business outcomes and capabilities you will actually benefit from when you have the data lake is the ability to, first of all, get new insights in your data that you didn't think you could have, because you end up keeping all that data and trying to analyze what business value you can extract. As well, by decoupling compute and storage, you can actually reduce your costs dramatically, because you're only initially paying for the storage of all that data, and we've got multi-tiered pricing. I will explain how that works. And then you only run the compute tasks when needed. As well, you end up using the right tools for the job. When you're doing big data analytics, you are using EMR. When you're doing BI analytics, you might use Redshift, or you might actually be analyzing files directly in the data lake. You'll be able to increase the durability and the security of your data. You will be able as well to charge back to your customers the storage they are actually using for specific data sets. And most importantly, you will actually be able to try doing something quite new, which is streaming and real-time analytics. But I think the biggest thing that actually comes out of having a data lake is the fact that you can retain all your data for years. You don't have to worry anymore about prioritizing your data or thinking, well, we don't have enough storage here. We have a limited SAN array, and there's only so much we can store, so let's only store some specific information we know we can use today. While with your data lake, you can actually keep any relevant information, and in maybe 5 years down the track, it's actually there. It might be in cold storage. You bring it back into your data lake, and you can actually start analyzing things. You may actually have new data scientists that can extract some value out of it. So, on to building our data lake. So by now, I think you've actually understood at a very high level the benefits of having a data lake, but beware, because if you actually design that badly and it's not managed properly, you will end up with the worst situation where you actually build a data swamp, and we really want to avoid this. So I'm actually going to share with you some design patterns and best practices to make sure that you actually have a very solid data lake. So first of all, let's talk about all the building blocks that will actually construct that data lake. First of all, we will have a storage and ingestion block that will be supplemented by the cataloging and search function. We will have security all around to actually protect our data. And we will talk about having an application programming interface and user interface block to be able to actually access that data or trigger some jobs. So on storage and ingestion, the requirements would be, first of all, the ability to store data for multiple years. It has to be very highly durable. We need to be able to store any source and format of data, and at the lowest cost possible. So if I was to actually interrogate you, if it was like an exam situation, you would know without having to think that we will be relying on key services like Amazon S3 and Amazon Glacier. So they are actually both providing scalability and durability, but they actually have lots of features in terms of security that will actually allow you to have things like S3 versioning, so you never delete your data and you can always understand what's happened with it. You can actually start using a multi-tier storage with different costs. So if some data has been captured and is stored in the data lake, but you know you might not need it for maybe a year, you can actually send that into Glacier. And there's lots of things that are actually captured on these slides. Don't worry, it's actually all available in the Summit app, and it will be available in a few weeks as a video. So if you don't have the time to take the notes, you can always leverage that in a few weeks' time. So we are going to start building a mental image in our minds of what the data lake will look like. So we have the storage layer with S3 and Glacier. Now to talk about some recommendations for storing the data. So first of all, we need to actually make sure we have the right things in place for S3 buckets. You need to actually put your S3 buckets in the right regions, so they are you're storing the data close to your users and especially close to the right compute. So if you want to actually run some EMR jobs at a specific cost, make sure it's actually all in the same region. But especially if you are operating in a regulated environment, you may actually want to use for ANZ customers, you may want to use the Sydney region and make sure that your data never leaves that region. The other thing that is important is naming conventions. You need to have naming paths where you will have the bucket names and folders and file names that are almost what I would call self-documenting, and that path needs to be humanly readable. The other thing you need to do is one of the best practices we've got for Amazon S3 that is documented on our website is the use of a random hash prefix in front of folders and file names. So you actually end up distributing your files across multiple S3 partitions, which will in turn actually enable a very high throughput. And that's very useful as an example if you're running an Elastic MapReduce cluster and you're actually sucking the data out of the data lake to actually feed that into your Hadoop nodes. So something important to keep in mind. The format of the data you're going to store is very important as well. So depending if it's structured or unstructured, you may actually want to use a specific data format, and you want to actually associate the compression with it. So I've put some keywords on the screen that are just more of a reminder for you. But in this case, let's say that if you're wanting to store some small CSV files, you may actually want to compress them with gzip. And on the other hand, if you start doing streaming analytics, you may want to actually use Parquet file for loading these streams into Spark. But at the same time, you may want to compress that with a format like Snappy. Second set of recommendations, we want to actually optimize that storage. So first of all, you need to make sure you store everything that has business value. But by storing everything, you need to actually be quite cognizant of what you are going to store and how. And the recommendation is usually to use large files that are in a splittable format. Lifecycle policies as well to actually reduce the cost. So if you know that some data doesn't need to be processed or analyzed after the first 3 months, but you may need it in the future, lifecycle policies will actually enable you to transfer that into Glacier. And as well, use tagging for cost allocations to be able to redistribute this cost to the right business units. Security is very important because we're talking about business data. Some of that data actually might contain confidential information. So use encryption across the board. Use bucket policies, access control lists, tagging as well to understand actually the ownership of that data. And remember to have CloudTrail enabled to capture all the access to our APIs and then understand what's happening with your data lake. I will have a dedicated section on security, so we will discuss a bit more. Now, part of our storage and ingestion block, let's talk about the ingestion in particular. So I would expect that you are all doing already batch file and ETL imports into S3 and maybe databases on AWS like RDS. So that's something you're quite familiar with. But there's actually the new concept of streaming data that will actually enable you to consume any data sets as a stream. So that data set could be clickstream analytics coming out of a mobile app, or it could be some data that is coming out of a mobile device or an IoT device. So you actually can capture that as a stream and analyze that in near real time. But the advantage of actually getting that ingestion mechanism into the data lake, you can actually capture these streams and store them in the data lake for later replayability. So the key services here for ingestion are actually under the banner of Amazon Kinesis, and we've got two flavors. We've got Firehose, and we've got Kinesis Streams. So Firehose is actually a great service that we released last October at reInvent. And the advantage of our Kinesis Streams, it's actually got the ability to run with an agent. It's a fully managed service, and it will actually capture things, let's say, like server logs running on-premise or in the AWS cloud. So it could be web server logs. So you would actually install the Kinesis agent and import that information, and you can actually distribute it simultaneously to S3. You can as well import it into Redshift and Elasticsearch. While Kinesis Stream is actually slightly less managed, and you actually access it with an API. So we have the Kinesis client library that you would have to integrate within your applications, and will actually enable you to consume the stream. So I will actually discuss how that would work differently. Just to give you an idea of how Kinesis works, on one end, you've got all your data sources. It could be your server logs. It could be mobile devices and their clickstream data. It could be IoT devices. And when you actually enable Kinesis, you will have Kinesis in a region. We create a stream for you that is across multiple availability zones. And your data producers will inject that streaming data into the stream. And at the back of that, in the AWS cloud, you can have your consumers that can be either the Kinesis client library, so that API SDK that you can actually import in your applications, or you can start consuming with serverless compute like Lambda. And as a result, you can actually store these streams into S3. You can actually import that streaming data into Redshift, do search with Elasticsearch. You can as well import that information into DynamoDB, which we are about to discuss. Or ultimately, you can actually have real-time analytics with our services like EMR and Apache Spark. So building our mental image of what it will look like, we will have our storage and ingestion block with S3 and Glacier, and it's being supplemented by Amazon Kinesis. The recommendations for ingestion, and especially streaming analytics. Streaming analytics is actually going to add complexity to your environment. So make sure that you've got the clearly defined business case, because it's actually not that simple to start doing real-time analytics. As well, you will want to select the right tools. So depending on what you're trying to achieve, you may want to look at Apache Spark running on EMR. You may want to investigate technologies like Storm and Flink. So all these things actually will allow you to do a big data streaming analytics. But at the same time, you may want to leverage some of the features we have already with our services, like the fact that Firehose can actually import simultaneously into Redshift, so you can have near real-time business intelligence and dashboard creation. As well, you can import that information into Elasticsearch managed service. And some tips here. You can actually use AWS Lambda to do some transformation on the fly of your streams, and you can use that to persist the streams into S3. And I'll tell you how you do this. So I've got two blog posts I'd like to share with you. The first one is from one of my colleagues, Derek, and he actually gives the details in this blog post on how to use AWS Lambda to capture information coming out of Kinesis Firehose and to persist that stream into S3. So as a result, you actually have that streaming data into S3 that is available almost like a file, and you can actually come and replay it. You can have multiple teams coming to actually analyze that information at the same time, and you can actually replay these analytics with a different model. The second blog post is actually the next stage of streaming analytics. So my colleague Amo, who is actually based in Sydney, explains how you would use Spark streaming to be able to actually query Kinesis streams directly with SQL queries. So the next layer, it's actually a very important layer. It's going to provide you the ability to catalog and search your data lake. And the reason why it's very important is because you will end up having sometimes billions of objects into S3. So that cataloging and search function will actually need to build a metadata index. So you need to actually capture the metadata of your S3 objects. It needs to be done in an automated way. So we want that to be serverless and event-driven. And we want to as well enable the ability to actually search, discover that data, and be able to do data classification with this. So what we will use is actually a combination of our services. Lambda, our serverless compute service, DynamoDB to actually store that metadata, and Elasticsearch to be able to actually search that metadata. So if we look at a diagram of how this works, Lambda will be triggered by objects landing into S3 or into Kinesis. So you actually get a notification of an object in S3 that will trigger a Lambda function, and that Lambda function will in turn analyze that S3 object, extract the metadata, and store that into DynamoDB. In that same Lambda function, you may actually want to start indexing the content of these objects, so you can actually search this, so you actually send that information into Amazon Elasticsearch for indexing. Now, if you actually want to bridge the gap and be able to search the metadata index directly, you actually need to enable the Logstabs plugin as well as Kinesis streams. And this, in turn, you will actually be able to search the metadata index and even create dashboards using Kibana. So remember how that will work, because it will actually be the secret sauce on top of your data lake. And that's what Namjay is actually about to demonstrate later. Some recommendations for cataloging and search. So first of all, start small. I would say in the first occurrence, when you start cataloging your information, think about maybe capturing file names and size and dates and the owners. And then at a later stage, when you're more comfortable with the technology, you can actually augment that by having a data lake that is across multiple regions. So you have a metadata index that will capture the region of the object, maybe information about versioning, lineage, and relationships of objects between themselves. And what you need to decide as well is, do you want to search just that metadata into DynamoDB, or do you want to search the object content as well? Because if you've got an ginormous data lake, you may not want to actually index the object content into Elasticsearch, because you will end up having a very, very large cluster. So most importantly, indexing the metadata is what you're actually trying to do. And try to actually be aware of the events that will be triggering these Lambda functions. So on one end, as I said, you actually can have S3 sending notification when an object is being created or modified, to in turn actually trigger a Lambda function that could maybe do some processing and transformation or copy into another region or a bucket. And DynamoDB streams is actually an ability for DynamoDB to give you information that you can extract to either replicate this information that is in Dynamo, or to actually inject that data into the Logstash plugin for it to be indexed into Elasticsearch. Two more blog posts I'd like to share with you. This is really much the secret sauce. The first one from Mike here is explaining how to actually build the metadata index using Lambda. So it's pretty much what the demo will be about. And the second blog post from Asaf is actually explaining how you use the Amazon Elasticsearch as a service to be able to query in real time things like Kinesis firewalls, and using Lambda to do this. Very important block as usual, because we're talking about your data, it's going to be the security. And the requirements there are actually pretty simple. They're usually what we would recommend for any of our services. Use data encryption at rest, because we're trying to actually protect some potentially confidential data, and try to think about authentication and authorization. So the usual suspects here are identity and access management, as well as our key management service. So for IAM, you'll be able to create users and roles and groups for your end users who may want to actually access the data lake. But what you want to do as well, at some point, you actually want to have identity federation with a corporate directory. It will enable you to have granular permission, and then in turn, you will actually integrate with KMS that will manage your encryption keys. And we have actually multiple ways to do encryption on S3. We can use server-side encryption, which is actually quite simple. And then on the other end of the scale, we have our Cloud HSM service, which actually allows you to provision a hardware instance. So it's actually a hardware security module where your customer keys will actually be saved in. I think it's Probably important to focus on KMS because KMS tends to plug into all our services, and it's actually the right balance between key management for our customers and complexity. A simple block once again. And the recommendation for security, start early, because security needs practice. The concept of key management and encryptions are actually not that simple. And especially if you start thinking, okay, do we want to encrypt that data using server-side encryption? Do we want to actually rely on the AWS service to do the encryption using our key in KMS? Do we want to encrypt that on the client? So we actually encrypt maybe on-premise or in some EC2 instances, and then only then we send it to the data lake? That's some of the questions you will need to ask yourselves. The other thing as well is you probably want to federate with your corporate directory. So the usual suspect here is Active Directory. Because initially you may have a subset of users that you allow to access data into your data lake. But if you start having hundreds of analysts that need to actually leverage your infrastructure, it's probably easier to have identity federation with Active Directory. Once again, to improve your security, the usual best practices, use CloudTrail to log all your API calls, and use CloudWatch to monitor what's happening with your data lake. Encrypt where possible, very important. Although, be mindful of what you encrypt because there are some cases where it will be detrimental. An example, if you are actually encrypting some data that doesn't contain anything really confidential and you are planning to load that into EMR, there will actually be a decryption overhead when your cluster nodes need to actually do the job. And as I said earlier, make sure that you select the right regions and buckets for regulatory compliance. Some more tips. Use IAM policies, S3 versioning to be able to find out what's happening with your object in S3. And another one that sometimes people actually are not aware of is the concept of having a multi-factor authentication token to be able to enable delete. So you may actually want to tag some buckets to force end users or especially analysts to use a specific token so they can actually get access to that data and delete it. And just food for thoughts, Lambda, the serverless compute service, why not use that for data masking? So an example, you may have some data on premise that contains some personally identifiable information, PII data, and you may actually want to load that with Kinesis firewalls, and you trigger a Lambda function on the fly that will actually modify the information to actually do some obfuscation of anything that is confidential. And last but not least is actually the API and UI block. So initially, you will probably have your analysts accessing the data lake directly by having access to S3 or with a compute layer like Redshift. But as you move forward and you have billions of objects and you're having a very complex data environment, you will want to actually have a pretty solid API and UI layer because it will enable you to actually serve data and capabilities to your customers. So an example, you may actually have a user interface that will allow you to start EMR jobs on top of your S3 data to be able to actually do big data analytics. But what's important with that layer is you want to do that programmatically. Instead of having your users interactively connecting to your data, at some point you may want to actually create a very dedicated API that will be loaded into some of your enterprise application to access that data. Or the other thing, you may actually want to have an API gateway to be able to access that data through RESTful endpoints. And that API and UI will as well allow you to have an extended control and management. The other thing, it will allow you to have familiar use of visualization tools like Business Object, Tableau, and whatever you use for your SQL queries. So how would that work? First of all, we will combine API gateway, which is actually an API service that is able to perform at any scale. And what it does, it creates some RESTful front ends for either your own services or AWS services. So you end up having a situation where you have your API gateway front end that may actually trigger some Lambda functions to maybe start doing some processing or batch work, or may even start a Docker cluster to be able to do long-running batch jobs that might last more than 5 minutes, which is actually the compute limit of Lambda. the execution limit. And the combination of API Gateway and Lambda is actually very well thought through because it can actually perform at any scale. So if you've got hundreds of users or even maybe thousands of users accessing your data lake, it will be able to cope with the demand. Once again, simple block with just 2 services. And the recommendation for these services is try to go serverless where possible. And that means use AWS Lambda to actually extend existing AWS services. There might be cases where our services actually are missing a very specific feature or maybe an automation you want to do. Code that and create your business custom logic with Lambda. You may want to use Lambda as well for data management, processing, and transformations, or copying the data between buckets or doing all sorts of bad jobs. And the association of the API gateway for data access is actually very powerful because you end up in a situation where you have actually a RESTful API and you can create an SDK that you can not only use internally, but you can actually distribute that externally. So an example is for public sector customers, you may actually have a data lake that contains information that needs to be actually accessed through, by multiple departments and third-party customers. So instead of actually giving them IAM access and so on, you actually give them access through an SDK. And most importantly, with the API and UI layer, you can actually start extending the solution and building advanced security controls. And these security controls would then be, in turn, stored into the metadata index. So going on to the whole picture, we are going to start again with our peaceful lake. And we have our storage and ingestion block, S3 at the heart of the storage block, and Kinesis for any streaming data. This is being supplemented by the cataloging and search function that will be actually triggered by Lambda, loads the metadata index into DynamoDB, and enable you search capabilities with managed Amazon Elasticsearch. Security across all our services is very important. And then, when you start feeling comfortable with your proof of concept, build that API and UI layer. Once you're there, you can actually have multiple ways of accessing that data through what I would call the compute layer. So that data, you may want to actually import it into our petabyte scale data warehouse, Redshift, to be able to run your BI tools. Or you may want to actually extract a subset into our relational database service, RDS. Or you may want to run EMR big data batch jobs. And ultimately, your users will be able to access that data either through the UI and API. They can query the catalog, or they can actually go through the compute layer to have a specific subset of data that they can actually interrogate. So, in summary, the data lake is actually a foundation of durable data storage and streaming data that is complemented by a metadata index that will enable you categorization and governance for that data. It will actually as well give you a search index. You will have very robust sets of security controls to make sure that no data gets leaked out of the lake. You will actually enforce security through technology and not just policy, because everything is actually being hard-coded in terms of security controls and then access through the API and so on. So it's not just written policies, it's actually technology enforcing the security and governance. And you will have the interface to actually expose that data and capabilities to users, either internally or externally. So now I'd like to invite Namje for the demo. Thank you.
Cool. Thanks, Sebastian. Okay. Good afternoon, everyone. Can you hear me okay? Cool. I don't have as a cool accent as Sebastian, but I'll try my best to do a great demo for you today. So my name is Namje, and I'm a solutions architect based out of our Sydney office. And I'm going to take you through a short demo of the catalog and search component of the serverless data lake that Sebastian described today. But before I dive into the demo, let me spend a couple of minutes to tell you about the demo set up today. Now, the data flow on this diagram is from left to right, starting with the data source. Now, I've built a very simple Java program, which will push data objects into our S3 bucket, which is effectively your data lake. And then we've got S3 events set up on that bucket so that every time an object lands in that S3 bucket, a Lambda function will be executed. And when that Lambda function executes, it'll pass the object name of those objects landing in S3 bucket, and then it'll push that data into our DynamoDB table. And DynamoDB table is effectively our metadata index. And then on the DynamoDB table, we've enabled DynamoDB streams. And what that will allow us to do is use the Logstash to subscribe to the streams, and then subscribe to the data that's landing in DynamoDB table, and then push that data into our Elasticsearch cluster. Now, once the data resides in Elasticsearch, you can use that data to essentially visualize and create dashboards using the Kibana tool that comes integrated with our Elasticsearch service. So without further delay, let's jump into the demo. Switch screens, please. Okay, can everybody see that? Awesome. So what you're seeing on screen at the moment is our visual designer for the CloudFormation. So what I'm going to show you is how simple it is to actually create the entire search and catalog functionality, or the component, with a single CloudFormation template. So I'm just going to kick that off directly from the visual designer. Loading, and then going to the next screen. Then I'm just going to call that Auckland live demo session. I'm going to call it 10. And then go next. And then acknowledge that it's going to create an IAM resource, and then create. And then if I refresh that, there is the stack starting to create. Now, this stack takes about 5-10 minutes to complete. So like in all cooking shows, I've prepared a stack earlier so that we don't waste any time. So moving on to my data generator, I'm going to kick off this simple Java program, which will start pumping data into the S3 bucket. And then I'm going to say simulate 5 servers, pushing 5 objects per second. And again, this takes about 10-15 seconds to start pushing data into an S3 bucket. And there it goes. So 50 objects in 9 seconds. So from here, I'm going to move on to showing you the S3 bucket. So if I refresh the S3 bucket where I've defined as pushing the data into, and you can start to see that the data is landing in our S3 bucket. And this is effectively your data lake. So very easy. So I'm just going to drill down into one of these folders until we find a data object, and there it is. So with a very nice key name structure and a random hashtag pre-appended to the key name. And then from here, this should now start triggering the Lambda functions. So let me show you what that looks like. So if I start refreshing this, and then before I actually move on from this screen, I just want to quickly show you that S3 bucket where I'm pushing the data into is what the Lambda trigger is associated with. Now, if I refresh the invocation count, it's probably hard to see that there, but if I go to the next screen, which this is your CloudWatch metrics, and every time a Lambda function executes, it will basically put an entry into our CloudWatch metrics. And that little dot there, if I could enlarge that, is essentially, let me try refreshing that. There you go. So it's telling me that there's been 282 invocations of the Lambda function since I've kicked off that data injection program. So moving on to just quickly showing you, if I refresh this particular screen, this is our CloudWatch logs. So that with Lambda functions, you can actually also push your execution logs for every execution of the Lambda function into CloudWatch logs. And if I drill down to one of these logs, you can see here that it's starting to push into the index of our DynamoDB. And then moving on to, if I refresh, this is our console for DynamoDB. And then if I refresh that, now you can see the data landing. And the most important aspect, or the attribute within each of these items, is the key name, which matches up to what's sitting in at your S3 bucket. Now, before we move on to the next screen, I just wanted to quickly show you that Sebastian was talking about the DynamoDB streams. You have to explicitly enable this particular functionality within the table. Otherwise, it will not make the data available in the streams. So here's my Elasticsearch cluster running on AWS. So I'm just going to quickly refresh that. And then we've got the monitoring here as well. But rather than showing you this screen, I'm going to go to our Kibana. And I'm going to quickly do a search on Kibana on a known keyword called custID. And you can see with the histogram on the right here, which is showing you that data has started landing in our Elasticsearch Kibana dashboard. Now, that end-to-end demo probably took about 5 minutes. That is essentially the search and catalog functionality of our serverless data lake. But before I go off the stage, I just want to reiterate that what I've built there is a common pattern for a lot of data analytics scenario, and not just for a metadata indexing of your serverless data lake. So if you have any questions about how to build that particular component within AWS, come and have a chat with us after the session. But thank you for your time. And at this point, I would like to welcome Chris Riddell from Parrot Analytics to the stage. Thank you. Cheers, mate. Thank you.
Thank you. Thank you, Namjay and Sebastian. So my name's Chris Riddell, and I'm the co-founder of Parrot Analytics and the senior software engineer there. So I want to tell you a little bit today about our New Zealand, Auckland-based startup, about 5 years old, and a little bit about two of the best practice architectures that we use. One's going to be about streaming, and one's going to be about batch processing, and how they are used in our organization, and how maybe you can use them as well. So first off, a bit about us. We started out in quite a different place. We started looking at all these different types of data sources, and we looked at a couple of different industries. We looked at TV, we looked at movies, we looked at music. And we noticed that with the TV industry, there was, and there is, a very old paradigm of measurement. So things like surveys, panel-based measurement, are being used to decide whether or not a TV show is good. Of course, that misses out a huge demographic of an audience. That misses out anyone who uses the internet or web streaming platforms, or as we call them in the industry, OTT, over-the-top platforms, and as we call on-the-box TV, linear. So as you can see here with Dad watching linear TV and the kid watching Netflix, they're being quite hard to measure these two at the same time. Because of this fragmentation of the different platforms and the global proliferation of different types of platforms, it's becoming increasingly difficult to measure. So we set out to try and solve that problem, and we've created a demand rating system. So what we essentially do is we collect a number of data sources, so from social media to file sharing and wiki sites, and we basically rank all of these user signals that we receive from these different public data sources. And we say, for example, a like on Facebook, that might be worth 1 point. And a comment on Facebook, that's a little bit harder, might be worth 5 points. And so on and so forth for things like downloads of a piece of content and for things like purchases of a piece of content. Of course, that's a little more complicated in reality, but that's basically how we generate our empirical measure that we've created within the company called our demand expressions. Demand expressions are an industry-first measure of demand that helps you to measure how a TV show is doing within a certain country. So I can see here we've got Dino Trucks with about 1.6 million demand expressions. Remember, this is the aggregate of all these user signals. And in comparison to a show like Earth's Mightiest Hero, seems to have about half of the demand, so it's about half as good. We've also created a rating called our Parrot Demand Rating, which is meant to be a very simple to understand measure from 0 to 100, which helps you to decide how a TV show is doing relative to other countries. So we can see here in the example that Germany has more demand for Dino Trucks than in Australia, because of the difference in ratings. And the difference between a 43 and a 49 is a significant difference. Here's another example of some analyses we did. So it's quite typical of when TV show seasons are released to get a large spike in their demand. So we see here with the blue dot is House of Cards, and the red dot is where Daredevil's seasons were released. And we see a big spike there, and then it kind of tapers off. So that's quite typical of when we have season releases. Another thing about this is that these shows like House of Cards, which are Netflix original series, are incredibly hard to track in the industry. Netflix doesn't release how these shows are doing to other companies, so it's very difficult for them to say how a show is doing in comparison to those titles they don't know about. And to give you an idea about the scale of what we do, we calculate about 1.25 billion demand expressions daily from billions of interactions that we collect and aggregate on a daily basis. We have data in every ISO-listed country, and we have data on over 30,000 TV series. We were named one of the 50 most powerful big data vendors in the world because of the innovation and depth and breadth of the analysis that we're able to do on this. And we've been named one of TV's 5 hottest startups in the industry at the World TV Conference, MIP-TV. So without further ado, let's look at some of these architectures. And I'm going to talk in context of a log data architecture here when we look at an example of streaming analytics. However, this approach and this pattern that we'll see is also applicable for all sorts of other streaming use cases, sensor data, IoT, big amount of ingested data coming in now. We didn't have this type of problem before, now we do. Clickstream data, so again, as you click, data coming in, you may want to analyze that in real time. So when people start saying they want to have real-time analytics, that's when you start thinking about streaming. That's very difficult to do with batch. And anything where you want to react to certain events, so where time is of the essence. So if you have a log event where you want the alarms in your building to start going off when this event happens, then you need to think about streaming analytics, processing that as you receive it in real time. And as well, anything with constant incoming data. So sometimes we have types of data that will have a constant ingestion rate at a certain, say GB per hour rate, and we may find it more efficient for us to process that immediately because it's just constantly coming in than it would be to save it and then do it in batch. Now, this is what an architecture like this might have looked like prior to reInvent in October 2015, and we'll talk about the after that in a moment. But what we have here in our architecture is on the left, we have our EC2 instances, which are our log generating applications. So they're not necessarily a part of this architecture, but they're just there to demonstrate that we're generating some logs. And it wouldn't have to be EC2. You could also use things like, this could also be Lambda, or it could be a representation of your CloudTrail or S3 logs that you want to ingest and process. So those are going in here into the Kinesis Stream service, which of course is a big data buffering service. And the important part here is that we have our EC2 Kinesis workers, which are, we've had to write our own code, and we've deployed it onto our Kinesis workers, and those Kinesis workers are pulling out of that data out of the Kinesis stream and doing our aggregations and processing, whatever, and then pushing that data off into S3 and Elasticsearch running on an EC2 instance, in this case, which is our analytics store. Now, at reInvent, we had the release of Kinesis Firehose and the Elasticsearch service. So this architecture actually gets a bit simpler and a much lower barrier to entry. So we've got our log generating applications as before, and now we have Kinesis Firehose. So a big difference with Kinesis Firehose and Kinesis Streams. With Kinesis Streams, you're pulling your data out. With Kinesis Firehose, the data is being pushed out for you at a buffered interval, which you specify. So in this case, the integrations with Firehose are Elasticsearch, S3, and Redshift is also available. So we've decided to push our raw data into Firehose and then have it pushed for us into the Elasticsearch service and S3. We may optionally choose as well with Kinesis Firehose to compress that data on the fly as it gets pushed into S3, or to have some sort of encryption enabled on the fly as well as it's processed. Okay, so on to the second use case, which is triggered batch processing. So we're going to talk about this in the context of data dumps. so data dumps from something into S3. So let's say maybe you had a file that you've, or a user you've given permission to drop data into S3, and then you want something to happen now that you've got that data. You want some processing to happen. So that's the architecture we're going to look at, but also applicable for this kind of pattern is something like triggering jobs at responsive intervals. So that is to say, whenever we have something happen, like a file drop in S3, we want to be able to trigger something to happen in that case. Of course, anything that's cron style, so whether it be hourly or daily or whatever, this would be a good use case for that. And initial data loads. So EMR is frequently used when you've got an initial data load, you've got a big batch of processing to do at once. You maybe don't need to do that on an ongoing basis, but this would be a good architecture for that. So here it is. As you can see, we've got our S3 bucket on the left, and we've got a document going down into our S3 bucket, which is then being, of course, detected by Lambda as having been dropped there. We're going to run our own Lambda job. As you can see, we're using Lambda as a bit of glue between our applications here. And Lambda is going to spin up an EMR cluster. Our EMR cluster is going to then pull that data back out of S3, or rather out of S3, and it's going to do whatever aggregations and processing that we want to do on that data. And we've selected here that we'll have that data output into Redshift or into DynamoDB. So with EMR, of course, it's an Amazon product, but it's built on the Hadoop ecosystem of products, open source community. So it supports all of the big data technologies that you might have heard of, like Spark and Impala and Presto. You can use anything on it. And you can also make it work in steps. So you can have it spin up and run and then shut itself down when it's completed. Of course, I've selected Redshift and DynamoDB as the output points, but they could be anything. With EMR, of course, all the libraries exist for you to output into anything, and especially AWS ecosystem of products. So what next? Looking at some further features. Now, there are many further features you could add, from bucket policies and to anything else. But specifically zoning in on Lambda, again, with a few new developments of Lambda. We heard a bit about it at the keynote, and we know that it's now been released in Sydney. So some of the things we might do with Lambda, let's say we want to have alerts when we've batched or we've streamed something in and something's failed. Maybe we want those alarms to go off in the building. Or maybe we want to send an email out that we're completed. Maybe we want to send a notification of some kind. Another good thing, which is fun to do with Lambda, is, as you'll know if you're using CloudTrail or S3 logs, which maybe you should be if you're not, they're given to you in a raw dump format. So you could use Lambda to, when they get dropped there, then ingest those into analytics store that you can use, and then you can use that to audit those API calls into Lambda, into something like Elasticsearch, where they then become useful to you. Or maybe cron-style things like just deleting old Elasticsearch indexes or old data that you no longer need. And of course, anywhere else that you need some glue between applications, but it's not worth spinning up a server for. So that's all the content that I have for you today. If you have any questions or would like to speak to me more about any of those things, you can tweet to me at Chris J. Riddell or at Parrot Analytics for the company, or chris@parrotanalytics.com. We are hiring intermediate and senior engineers at the link there. Thank you very much for your time.
Thank you, Chris.
Thank you.
Thank you very much. It's really amazing to see what you guys actually in New Zealand are doing, and you are innovating at a global scale. So on to our next steps. I think you actually get a broad idea of what the data lake is going to be like now. And I have to say it's actually quite funny because I'm in the city of sales and I come to discuss data lakes with you. And we started with the Olympic pool. We talked about the data swamp. And then we're actually talking about the data lake. Maybe in a few years' time I might come back here and talk about data oceans with you. Who knows? But it's like anything. We need to start to run. We need to start to walk before we run. So we are going to start small, and we're actually going to build a data puddle. And the next steps for this to happen, go to our documentation. We've got AWS documentation that is actually extremely well written and is going to actually help you kickstart all the information we've actually shared today. There are some great getting started guides in our documentation sets. The other thing as well, think training and certification. Like the next stage for your data lake is probably going to be big data analytics. And we've got a great instructor-led training. It's a 3-day training called Big Data on AWS. And I will actually teach you all the ins and outs of EMR, Redshift, DynamoDB. I really recommend it. If you don't have internal capabilities, call for help. So we have a fantastic AWS partner network who are actually very familiar with this type of technologies. They can come and help you. And ultimately, we've got professional services members in ANZ who can actually help you build and design your data lake. I would think that by this time of the day, you've already visited our training and certification pod. So we'll just skip through this. I'm glad that nobody actually left the room. So thank you, everyone, for staying that late. I would really like to invite you to actually provide feedback, even if it's only 1 star, because without the feedback, I will not get paid this month. I remind you about the Tech Chat, our new podcast that are being kickstarted, and thank you very much.